Property number 6. In 3 dimensions, the delta function delta of r vector. This is the r vector in 3 dimensions. Okay, so in Cartesian coordinates, it has components xi cap plus yj cap plus zk cap. Okay, so in 3 dimensions, it has the components x, y, and z in Cartesian coordinates. Is interpreted as delta x multiplied by delta y multiplied by delta z. So in 3 dimensions, the delta function delta of r is interpreted as delta x multiplied by delta y multiplied by delta z. So it describes a function localized at the origin. Localized at the origin. Localized at the origin with unit integrated weight irrespective of the coordinate system in use. For example, in Cartesian coordinates integration, here delta r vector dx, dy, dz, this should be equal to 1. Okay. This is the function localized at the origin with unit integrated weight irrespective of the coordinate system in use from -infinity to +infinity. Okay. Or if you want to write in terms of this -infinity to +infinity, this is for x from -infinity to +infinity, y from -infinity to +infinity, z from -infinity to +infinity. Okay, and if you want to write it in terms of some function f of r2 vector, delta r2 minus r1 vector. Okay, then this would be dx2, we're integrating over r2, dx2, dy2, dz2, this is equal to f of r1 vector. Here dx2, dy2, dz2 are all integrated over from -infinity to +infinity. This is actually triple integral. Okay, this is actually triple integral from x from -infinity to +infinity, y from -infinity to +infinity, z from -infinity to +infinity. So x from -infinity to +infinity, y from -infinity to +infinity, z from -infinity to +infinity. Okay, in spherical polar coordinates, we can also write in spherical polar coordinates. In spherical polar coordinates, this can also be written as triple integral f of r2 delta r2 minus r1. Okay, here we have r square, this is r2 square dr2 sine theta 2 d theta 2 d phi 2. This is equal to f of r1. This r square sine theta dr d theta d phi. This is the volume element in spherical polar coordinates. I repeat, r square sine theta dr d theta d phi. This is the volume element in spherical polar coordinates. So we have the extra terms r square sine theta. Okay, and here r2, the range of r2 is from 0 to infinity. The range of theta 2 is from 0 to pi. The range of phi 2 is from 0 to twice pi. Okay, this is fine. And then we come to the last property of Dirac delta function. So the last property is property number 7. That is the Dirac delta function in this is equal to minus infinity to plus infinity exp, the exponent of I omega t minus x d omega. Here we are integrating over omega, and what remains is t minus x. Here, with the understanding that this has meaning only when under an integral sign. Under an integral sign. Okay, this delta function, it can be represented like this with the understanding that this has meaning only when under an integral sign. That means when this term is integrated over. And in this context, it is extremely useful for simplifications of Fourier integrals. When you learn Fourier integrals, you will find this to be extremely useful. Okay, that is it. That's all about the properties of Dirac delta function. So let me stop the recording here.